In this video lecture, we shall start by giving the general form of a linear mixed effects model. So we shall start with our familiar fixed effects model, which was something like this. So we had this y vector, this is our y vector, the blue vector, that equal the x matrix, the red matrix, multiplied with the beta vector, that is this red vector, plus this purple thing, that was the epsilon vector, the error vector. Now the way we introduced this mixed effects model was saying that we will take certain elements of this beta vector and just say that those elements are random quantities. So we take some of them, say things that I am showing with green in that beta vector, and I say the green things are random. Now observe that these green things are controlling certain columns of the design matrix. So each column of the design matrix is devoted to one of these coefficients in beta. So whenever I say that these and these are random, there are corresponding columns of X which are dedicated to those particular entries of beta. Now when I am doing this multiplication, what I am doing is basically red times red plus green times green. So when I am doing this matrix times vector multiplication, that's what I am doing. So what I can do is that I can write the same thing with all the red things put together and all the green things put together. So I had the two red columns, I put them side by side and I produce one red matrix, and I keep only the red part of the beta of my beta vector plus same thing, but now I work with the green things. So if I do that, I am expressing the same thing, but the fixed effects are stored as red and separately the random effects are shown as green, and the blue and the purple remains the same as before. Now in this way I will give some new names. So what I will do is I shall consider the red part of the design matrix X. So earlier the entire thing was X, but now I call only the red part X and its corresponding coefficient vector beta. Plus the green part of the design matrix I shall call that Z. Just like X, it is also a fixed known matrix, and the random part of that vector I will call that G. Basically it was beta and gamma, and since I use English letters for the random quantities, so I have used just G plus epsilon as before. So combining everything, I get the form y equal to x beta plus z g plus epsilon. Of course there should be a vector sign over epsilon also. So this is the general form of a linear mixed effects model. Now of course I need certain assumptions, distributional assumptions. So these are the distributional assumptions that I will make. I will say that epsilon as before follows normal, mean, zero, some variance. I will give a similar distribution for G also, and they will be independent. So I can pack all this thing in a single assumption, make G epsilon. So stack all these G things. So I will make this n by q and this is n by p. So G is a q by 1 thing. So I stack that q by 1 thing on top of my n by 1 epsilon. So I get something which is q plus n dimensional. It's a multivariate Gaussian with that thing. Observe that I am saying that these covariance terms are 0, which means that they are independent. Since I am assuming Gaussianity, mean is 0. And I assume that G has a covariance structure given by capital G and epsilon has a covariance structure given by R. What may look a little unmotivated is that I am taking common this sigma square, which is the common thing extracted out of both G and R. I am not saying this is G and that is this is sigma square and that is tau square. I am not saying that they have the same variance. So G and R need not be the correlation matrices. These are still covariance matrices, but this is something like the common scaling factor that I am drawing out. That's just a common usage That's the common notation. If you think that they have got different variances, that is fine. Just incorporate that additional constant in G or R separately. In many cases, we assume that G and R are just completely known and given. In certain cases, they may involve further parameters like some theta parameter. They may have compound symmetry structure or AR1 structure. In that case, G and R will have known forms involving unknown parameter theta. So this is the general form. Now observe that though it looks somewhat complicated possibly, however, this is nothing but our familiar linear model. Just consider this entire thing. This is the entire random thing. Call that, say, eta. If I call that eta, I will say this is my random part. Then this is nothing but our familiar linear model. Y equal to x beta plus eta. Now eta will have some complicated covariance structure, that's all. And it is pretty easy to compute the covariance structure. What is covariance of eta? The variance covariance matrix. It is the variance covariance matrix of this plus the variance covariance matrix of this, because there is no covariance between these two. So it will be Z times G times Z transpose plus R. So you can say that my eta has just this distribution, normal, now it is n-dimensional, zero mean, and covariance matrix is sigma squared times Z G Z transpose plus R. So whatever we have learned earlier still applies. So it is nothing really new. It is just a special case of that. So if you have a software which can fit a fixed effects linear model with some specified covariance structure, then the same program may be used to fit a mixed effects linear model as well. So far as algorithm or computational aspect goes, there is absolutely nothing new. We are still under the same umbrella. However, interpretation wise, the thing has changed a lot.